Okay, today we're going to talk about classification. I was actually trying to make sure that my network didn't go down, and so I tried to do this from CMU, but the network is down. So it's probably me, so I apologize if your network goes down. It's probably something to do with me. But today we're going to talk about classification. So this is one of the standard things that happens in natural language processing. We have some documents, we'd like to classify them in some way. Maybe you've got a bunch of news stories, we want to know whether they're politics, finance, arts and entertainment, sport, business, something like that. And so we're going to choose between some bunch of classes given the natural language document. Maybe this is sentiment. Maybe this is, we want to know about expressiveness. We want to know some aspect of sorting things into a relatively small finite class that we know beforehand, and we want to train from data in order to be able to do that. Okay, so what I'm going to do today is I'm going to go through a number of machine learning techniques that deal with classification. Okay, now this is quite a wide range of things, and I want you to understand the difference between them. Yeah, maybe you might end up using neural networks for things, but depending on the amount of data you have, depending on the type of data you have, sometimes that's not the best way of doing things. Okay. So a little bit about notation. We really are talking about machine learning today. In fact, most of what we'll be doing is really machine learning stuff. If you've done a machine learning class, you probably will know all of this already, though I will be a little bit doing this with respect to natural language processing. So we are talking about supervised learning here, and by supervised learning, we mean we have a training set, okay? And that means that there are going to be a bunch of examples. And so we're going to have a bunch of documents, and each of these documents will have pre-assigned to them their correct category, okay? We have to get that data from somewhere, and that means somebody has to label it. So it has to exist before we can actually do that. Sometimes you don't actually need it explicitly listed because actually implicitly it's got that information. So for example, if you were going to do looking at reviews on Amazon, and the reviews have stars, a number of stars, you can use the stars as the category, and you can say, I'd like to be able to predict the number of stars, and you have it for each of the different reviews that are actually there. But we're going to have examples, and we're going to have, for each of these examples, we're going to have the categories that have to go that. And again, I say a small finite number. Yeah, it could be hundreds, but it's probably 10s to 20s because that's usually the type of thing that you want to do, especially if you're actually doing discrete categories. What we want is a classifier, a function that will ultimately take an example and predict a Y, predict the category that it's in. So we will give it a document, and it will predict something like sports, finance, art and entertainment, politics, or whatever. It will predict what that is given the input. Okay, so this is a mathematical function. Okay, it's a Python function probably that's going to do this. Now, that function could be written by hand, so you could write a bunch of rules and you could try to do it. And for some things that works very well, and you could get quite a reasonable result. In fact, you could get a lot of control over things. And in spite of all this machine learning stuff that we actually do here and we all believe in a very big way, actually a lot of functions that are like this end up having a bunch of rules. They may have some machine learning component, but there's sort of, you know, careful bits that have rules in them as well. But let's ignore that for the time being and say we would like to have another function, L, that will generate C given a bunch of training examples. So if we have X and Y's, so we have a bunch of training examples of documents and their categories, it will learn some function which we can then apply to new examples that we've never seen before. Okay, so L is what we call a learner. It's a training mechanism, and the output of it is a function, C, that when applied to new examples of things like X, we will predict Y hopefully accurately. Typically, we don't do it completely accurately, but we'll be able to do it accurate at some level. Okay. Now, that function could generate a bunch of Python code, but typically it doesn't. What it actually does is it makes a decision about the type of model it's going to learn, and it outputs a bunch of weights based on that. And what we're going to talk about in today's lecture is a number of different ways of learning that function L and how we can restrict it in ways to be able to make it easy, and the consequences of that when we're actually trying to build a machine learning function that represents C. Okay. Now, first one I'm going to talk about is probabilistic classifiers. Okay. And so what we're really trying to do is, given X, given some sample, what we'd like to find out of which is the most likely class given that file. Okay, so is it politics because it's got the word Trump in it? Is it sport because it's got Steelers in it? Is it art and entertainment because it's got Enola Holmes in it, or whatever? So we can actually, might be something as easy as that, but it's probably something to do with a bunch of words and something to do with a bunch of weights, and we could find out what the most probable category is given the input. Sometimes it'll be confusable because it's in 2, but what we'd really like to do is, given an X, be able to get the maximum probability given the X that we predict whatever we think Y is. It might not be right, but it want it to be as right as often as possible. Okay. Now, how can we go about doing this? Well, we're again going to go back to our popular noisy channel that you've seen multiple times before. So what we're really trying to get is find the Y, find whatever thing we think gave rise to the document, actually sort of the inverse. And we can do that by the probability of Y. So it might be that there's more politics articles in the Wall Street Journal compared to art and entertainment in the Wall Street Journal. So there's some distributional property of what we expect the classes to be, but also what's the probability given that we see the document. So what's the probability of if it is art and entertainment, what's the probability of the word Trump appearing there? Or what's the probability if it's about politics that the word Holmes would appear? Or what's the probability of if it's about finance, the word Steelers would appear? Well, that one might be ambiguous. It could be about sports, but I suppose it might be, well, that may be Steeler or something instead. Okay, so we can have this function here. Okay, so given that we're looking for a probability, what we can actually do is decompose that with the Bayes rule into 2 forms. We're going to have probability of Y times the probability of X given Y. And we've said that that is the same as the probability of Y given X. But this is an easier way to train things to decompose it. And we can calculate for, say, a certain word. Okay, we can break things down into features for words. Actually, on Thursday, I'm going to talk about how to be able to get features and the sort of features you might, but features might be the existence of a word. Find out that if it's politics, what's the probability of Trump? If it's sports, what's the probability of Steelers? If it's art and entertainment, what's the probability of Holmes? Times the probability of these classes overall, given the domain that we're actually in. Okay, so that's a pretty standard way using the noisy channel model to be able to do a probabilistic model. A probabilistic, we're trying to get the most probable. Okay, now actually we are really talking about the representation of our documents, if they're, say, news articles, into a vector space. And that vector space is going to have a whole bunch of features in it. And they're probably going to be relatively sparse. They don't have to be. We'll be talking about dense representations later. But if you imagine that we choose a vocabulary, 10,000 words, and what we have is a vector space that has a 0 if that word never appears in the document, and a 1 if that word does appear in the document, and if you have about 10,000, you're going to get pretty good vocabulary that'll cover all the important words, maybe not novel words, but definitely a bunch of relatively important words for your domain. And what we can do is have that big long vector with zeros and ones in it, although most of them will be zeros because most words won't actually appear. And we can try and find out the relative weights of these things, and we can actually find out for each feature what's the probability of it being there, and multiply them all up, or maybe do the log probability, and we can add them all up and find out what the probability of the overall document is. That works pretty well, often, but it can be quite expensive, and it's sort of a waste. And there may be better features. There may be a way of selecting features of rather taking all the words that actually be much more efficient to do this. Often, in fact, a lot of the time, when you're building natural language systems, what you actually do is spend quite a lot of time trying to choose good features, okay? And sometimes some features are really good and some features are really confusing, and therefore they're good to drop because they actually don't help. They don't have that reliability. And so you can choose which features to use. So supposing, okay, we were trying to do a classification of a bunch of news documents into 5 classes: business, sport, politics, art and entertainment, and other. Can any of you come up with a good idea of what features we might want to have based on a document that could be useful in predicting either positively or negatively the result, because that's useful too. So can any of you suggest some features? So on the slides, we have bag of words, okay? That just means the occurrence of every word, but sometimes that's not really ideal because we get too many words. So maybe we want to get rid of the really common words like the and off, and we want to get the other words that are actually much more likely to actually distinguish things. Okay, and so we could look at the high frequency words, we could look at the high frequency words for the domain, we could actually do even more complex things of TF-IDF and find out the words which actually have got high instance within a particular domain and do not appear in other domains, so ones that are most distinguishing. So we could do things like that, but we could also consider things like the length of the document. We might also consider the title distinct from the document itself, because the title might have more information in it about what the subject is than what the actual content is, or it might be easier to be able to do it. So we could do a bunch of different things of trying to get the right representation for that, okay? Now, the probabilistic noisy channel model is only one way to do it, okay? And there are other ways that sometimes can be as efficient, and sometimes can be as successful, and sometimes can be easier to train, and sometimes can just be better, okay? And there's another standard model that lots of people use, which is called the naive Bayes classifier, okay? And what the naive Bayes classifier is, it's a bit like the probabilistic one, but it's not completely like the probabilistic one. We still do the probability of the class, but what we do is we do a probability of each of the features. Okay, so what we actually do is we go through and look at, say, all of these features and find out for arts, entertainment, finance, politics, sport, whether that feature, whatever feature we actually got, exists. And we take the product of all of these features. It's called naive because we treat all of these features as independent. And I'm just going to say that again, because that's actually a very important part. All of these features are treated independently, and we don't look at the co-occurrence of these features, which could make a big difference on whether something is actually in a class or not. Really, really, really could make a big difference, okay? And so it's just not independent looking at those, but treating them as independent is actually a rather naive way of looking at the features. So that's why we call it the naive Bayes classifier. Okay, so we are going to look at all of these features completely independently, and we're just going to take the product of them, and we're not going to care about co-occurrence, and we're not going to train anything. We could make a feature that looks at two features and join it together. We could do that, but this is very much into the feature engineering, and that can be actually very, very, very hard to find the best combinational features. And you sort of really want your machine learning system to do that for you. However, naive Bayes usually works pretty well. In fact, it's a bit embarrassing about how good naive Bayes actually is. And often people come up with naive Bayes as their baseline, and go, we'll just build a naive baseline and Bayes baseline and use that baseline rather than Bayes line, baseline with naive Bayes. And then you spend an awful lot of time trying to find something that's better, or at least significantly better. Often you can find some things that are better, but they're not really much better. And if you train for 3 days with buckets of different data, you might actually get 1% better. And that's actually typically not very much. It will not really change people's futures. So naive Bayes is very naive, but actually often it's quite good, and you should be aware of that. And often it's a good idea to train this first, so that you've got a good idea of what you're trying to beat. Also, if you get a good result with naive Bayes, it tells you something about the difficulty of the problem, okay? And the higher the score, the easier it is. It also tells you something about how easy it is to make it better. But also, if you discover that the naive Bayes one is incredibly bad, it probably means you don't want features based on just words. You want actually more interesting features because the words aren't telling you enough information to be able to do it. Or the task is just incredibly hard, okay? Which sometimes it is. And you have to think about some other way of being able to do the task. How do we get the probabilities? Well, it's relatively easy. All we actually do is we look at, for our training set, we look at the count of the number of each of the classes that we have, and we divide it by the number of samples that we have. So we basically end up with a probability of each of the classes. That's easy. Then for the probability, the second part, for the probability of a feature, what we actually do is we count the number of times that feature appears in a class. So what we do is, supposing our feature is the occurrence of the word Steelers, what we do is for every class, sports, we look at the occurrence of the word Steelers, or we look at politics, we look at the number of occurrence of Steelers. And what we do is we then divide it by the count for that particular class. Okay, so we're looking at the probability of that feature within that class, not the probability of that feature over the whole data, but the feature within that class. This is quite simple. I'm probably going into too much detail, but I do want to make it clear. It is simple, okay? It's naive even, but this model is often pretty good, okay? And imagine it gets you 70% on a task, okay? You probably won't get above 80%, okay? Even with the latest, fanciest techniques, okay? Because naive Bayes actually contains a lot of the most important features typically, and so you get a lot of the probability, okay? So be aware of that, and it's often a good thing to do first because it allows you to, well, one is there's good tools to actually do this for you, and very quickly you can get this result. Very quickly you can work out that there isn't something wrong with your data, and that you can get an idea of how easy and how hard it's going to be actually to try to make this go better, okay? Now, that's one particular way. So we've talked about a generalized probability. We talked about the specific naive Bayes way of doing it. But there are other ways of doing this, and we can build linear classifiers. And what linear classifiers are saying is, given all these features, instead of caring about the probability of each, What I'd actually like to do is I like to give them weights. Okay, and these weights can be positive or negative, actually to plus infinity or minus infinity, or maybe not as big as that, hopefully not as big as that. And what you end up with is you end up with a function, okay, that you can take all of your features and then you can multiply them by the weights, one for each feature, okay, and then you'll get a number. And if that number is above some threshold, we often try to make it so that it's above zero. We can say that it's that class is yes. If it's below or equal to zero, we say that it's not in that class, okay? So we're trying to predict a bunch of weights that allow us to, if we multiply and then add up all of these components, that we'll get either above zero or below zero, zero below, okay? And it turns out that there's actually relatively efficient ways to be able to estimate these weights from data. There's a number of things you have to be a little bit careful about. Sometimes it's impossible, especially if you've got extremely noisy features, it just might not be possible. But again, there are relatively efficient ways of trying to select from the features that you can build a linear classifier for and ignore the ones which are confusable or too confusable. Also, actually, most of the algorithms that try to get this weights require that none of the features are 100% correlated with each other. And you might think, oh, that's fine, that should be easy. And it isn't actually. You often get features that only have the values 0 and 1, and you find in your training set every single component has zeros and ones in exactly the same place. That means that feature is fully correlated with the other feature that has zeros and ones in exactly the same place. And when you try to calculate the weights, you usually end up with a matrix which you can't inverse. And when you can't get the inverse of the matrix, you can't typically get the weights. There are, again, ways around it. I mean, there are ways around it that allows you to be able to get rid of these correlated features, but it makes it a little bit more complex. But if you build a naive way of building linear classifiers, you run into that problem. And there are techniques often referred to as stepwise to try to find the best possible features in order and ignore the ones that no longer make a difference and end up with something that is almost certainly as good as you could ever get. It's actually not guaranteed to be, but it's really weird conditions when it's not. And it's really weird such that real data probably would never have these conditions, okay? So linear classifiers are basically, if you think about things here, imagine that there's two features and we plot them in two-dimensional space. What we're trying to find is a line that goes through there, okay, which can multiply the values of the features together, add them all up, that allows us to actually draw a line that allows us to distinguish between them, okay? So we're actually trying to find that line, okay, which perfectly differentiates between the green diamonds and the yellow stars. There's no guarantee that there is a line. In fact, in real data, there almost is very likely not. So what you're actually trying to do is you're actually trying to minimize the amount of error when you're doing this, okay? And there are techniques to try to boost this in ways to try to get better and better minimization. But in general, you're trying to minimize it. And if you have a reasonable split, a linear classifier can actually do quite well, okay? So if your data's up to it, linear classifiers can typically do quite well to be able to separate out pretty complex data that humans would not be able to look at the features and go, yep, that's an important one, I'll give that a 0.7. That one is definitely negatively correlated with my results, so I'll give that a minus 83. Yeah, we can't do that. But, this is what computers are for. They do this pretty well. If we were just going to look at one dimension, okay, in this case, the x-axis, so let's just call it the left to rightness because rather than use another x, you would get a line like that. And that's not a perfect one because we've got one yellow star on the wrong side, okay? But that's using one feature. And if we project them all down to one and only look at one feature, we're not going to get it right, okay? But basically what we're looking at is trying to get that line or whatever that form is with all of the features with the best um, weights. Now, linear classifiers will only give yes or no. They won't give A, B, or C. There is another form of linear classifier that's called regression, which predicts a floating point number, and so it will give an amount rather than a yes or no. And sometimes that's a good thing to do too. But what happens, remember what we're talking about here, is we are trying to classify news reports into 5 different forms. How could we use a linear classifier to do that? Well, actually what we do is we just build multiple linear classifiers. So we build a linear classifier for sports, a linear classifier for art and entertainment, a linear classifier for politics, and we just build them all. And then we see which one is the most likely. It's not clear what the most likely is, where we probably look at which ones are above the line, and if they're more above the line, probably, but there's no guarantee that the values are compatible across the different linear classifiers. So maybe you want another classifier to take the classifier numbers and choose which one is the most probable. But you build multiple classifiers is the simple way to do it, and it often works quite well. You do get this number out of it, and you have to make decisions to choose between these numbers. And as I say, the magnitudes of these numbers, the larger one might not be the best one. It often is, but you might want to have to care a little bit more about accuracy, and maybe you want to feed that into another classifier. The third one, so we've been talking about, well, 3 or 4 depending on the probabilistic one, and then the specific naive Bayes one, then the linear one. This last one, and actually I've got a bunch of other slides about this particular type, is called the perceptron learner. Okay. Now, what we do in the other ones, is we are trying to predict the output, and what we do is we're trying to work out from the inputs how to predict that output. And what we do is we try to get weights on the inputs, and we calculate probabilities naively in isolation from anything else. What the perception learner is doing is different. So what it does, it's a bit, for first approximation, like the linear one. It's trying to find the weights to predict the y. But the way it does it, rather than doing ordinary least squares and some matrix multiplication, naive matrix multiplication or inversion, what you do is you guess the weights. Yes, you guess the weights. Okay. Somebody's asked the question, do each class in the multiple linear classifier have its own set of weights? Yes, it does. So they're trained independently, okay? And that's actually quite important. Training them together would probably not work unless you had multiple layers of doing things. And that's what you might do in a neural net. So no, when you've got multiple linear classifiers, they're independently trained and have their own independent weights. Okay, that's a little naive because there could be some relationship between them, but no, they're trained independently. When we're looking at the perceptron, though, what we do is, instead of trying to train weights and get them out of a matrix multiplication, what we do is we guess them. We guess them. So what we do is we look at each particular example that we have, and we guess the result. Okay, we guess all of the weights, and then we calculate the result. Okay, and we then score that result about how good it is. Okay, did it get it right, and how right or wrong did it get it? So we take that y and we look effectively how much above or below the line it actually is. And what we then say is, well, our weights are wrong. Okay, and actually what we say is our weights are wrong this amount of number. And then naively, what we do is we look at the number of weights we have, we divide by y by the number of weights, and we change all of the weights, okay, by y divided by the error we got on the previous example. Like, what? So what you're doing is you take an example, you have got some seeded weights to begin with. You're going to share the weights over all of the examples. You take the weights, and what you do is you calculate what the error is on y, and you take that error on y and divide it naively by the number of weights, okay? And you assign, you change the weights based on what you just divided with the error is. So you spread the error over the weights. So in other words, if y is too high, what you're going to do is you're going to take all the weights and make them a little bit more negative. If y is too low, what you're going to do is you're going to increase the weights a little bit. The general idea is that if we go through each of the examples and modify the weights each time, eventually the weights will converge on something that will minimize the error for y. Now, it's a little bit more complex than that, okay? That taking the error and putting it back on the weights is called back propagation. You've probably heard that if anybody's talked about neural nets to you before. What's a little bit interesting about the perceptron is it's actually doing a technique called abduction. It's actually saying, I think this is right, and I'm going to take everything and I'm going to weight everything until I get it right, which is very different from everything else is really going from the other direction, okay? Now, you actually can't just take all of the error in y and divide by the number of w's and do it. You can't do that in big steps because the weights will just bounce all over the place and they'll never converge. So you maybe only want to move the weights 1% of the error every time, or some percentage of the error, or maybe a lot percent to begin with, and then settle down as you get better. And there's an awful lot of different ways of trying to back propagate those weights onto, the error onto the weights. Now, although this may sound weird, it actually works surprisingly well. It also actually allows you to find non-linear solutions, which is actually quite interesting, because we talked about trying to draw a line in the linear case, but actually what we can get here is something that's a little bit more complex than a line. Now, maybe not in the simplest case, but this type of learning allows us to get non-linear prediction. But that's pretty good because actually most tasks are non-linear. In fact, most tasks are really not linear at all. You might think this is a new hip thing in neural nets and that it's only happened in the last 5 years, but no, the perceptron's from 1950 something, okay? It's even older than me. In fact, well, okay, linear regression has been around for about 300 years. Naive Bayes, well, Mr. Bayes was 1790 or something. So these things have been along for a lot longer, but actually computationally, perceptrons are actually been around for an awful long time. This type of learner started work in computationally in the 50s and 60s, and it has these interesting learning properties that can actually be quite good, and you want to be careful about how you do the weights, and a bunch of interesting math has come out in order to be able to help you to do that, okay? But that fundamentally is what neural networks are. Neural networks, if they are the simplest neural network model where you have a bunch of inputs going to a bunch of outputs as drawn in that linear form, where we have all of our x's and all of our y's, and we have weights coming from each of those going to weights of all of the output types, politics, science, sports, etc. And what we're trying to do is we're trying to learn all of these weights, okay, and modify them as we train by looking at the error and being able to boost or attenuate the values that are coming into it. Neural networks were like this from the 60s, 70s, maybe into the 80s. Yeah, 80s, we started doing interesting things. Actually, when Geoff Hinton finished his PhD, he started looking at actually more interesting things. A lot of people were looking at neural networks with respect to human neurals in the brain. And so a lot of the early work was fundamentally trying to model human neurons or animal neurons. But the machine learning people, particularly Geoff Hinton and a bunch of other people in the 80s, started using them for various machine learning tasks and found they could be pretty powerful. They would take an awful long time to train. And that's maybe why people found them entertaining or interesting, but didn't actually take over the world. And that's also because they had about the same properties and accuracy as many of the other models, like the noisy channel model or naive Bayes. But to be fair to neural nets, we didn't have much training data back then. Or if we did have much training data, our computers weren't very fast, and it would have taken far too long to actually train anything with them using the neural net technology we'd like to do. And so in the 1980s, if we trained something then with all the data we have, it might be finished by now. And remember, there just wasn't things like Wikipedia then. I remember one of the large natural language corpora that was in the 80s is a corpus called the Brown corpus. And I remember we got it at Edinburgh University in the 80s, and I was sent on a magnetic tape that was already old in those days. And because, even then I was one of these old people with a long gray beard. I didn't have a long gray beard then. I was one of the old people that came to me and said, "Can you read this tape?" And so I read the tape and loaded everything off it. And I thought there was something wrong with the tape because actually the whole corpus fit in my Emacs buffer in one file because that's what the whole corpus was. And I expected this was going to take at least megabytes and maybe gigabytes, although we maybe didn't have gigabytes in those days. So corpora were very, very small. It was really no bigger than a large Wikipedia article, one article, not the 10 million articles that we actually have in the large Wikipedia articles that we have now. But people would train, and then they decide, well, these neural networks are pretty interesting, okay? And really what we're trying to do is we can look at this as matrix multiplication. We're looking for these weights, and we say we're going to multiply them by the input, and then we're going to look at the y's. And so actually we can calculate, and that is just linear regression. But actually you can do something a little bit more interesting with neural nets. You don't just have to have one layer, you can have multiple layers. And these layers can be different sizes, okay? Now, of course, when you make these suggestions, the linear regression people might say to you, why would you do that? You'll lose information. And the neural network people who didn't know yet would say, well, maybe you could compress information from that. And then the linear regression people would go, well, no, you couldn't, could you? And there was a bunch of math and there was a bunch of investigation. And the answer is actually, yeah, you can. And people started doing it. And of course, now computers in the 90s got a lot faster. And so we could have more layers and we could have more data. But even the 90s weren't that long. And it was still very, very, very slow to train. And therefore, the types of problems that were being done were a little bit toy problems. And all the people using HMMs and naive Bayes were building on bigger amounts of data and actually getting on fine. And although there were still neural network papers that sort of worked, and they did, if you go back, they really did sort of work. People didn't get into them as much, but the multiple layer thing, people were looking at it. Now, oh, right, okay, I'm not getting into that. I'll come back to that later. Can I get to that? Yes, I do. So this compression thing is actually quite interesting, and people didn't really take advantage of it until really into the 2000s and 2010. So if you took something like a whole bunch of features of the input and you compressed them down to significantly smaller feature set in the middle, so imagine you had 10,000 words and you had zeros and ones as your x's coming in, and that length of the vector here, okay, was 10,000. And here we reduced it down to, let's say, 300, okay? And then we tried to predict x again with all the zeros and ones in the same place. we actually could get a compression algorithm, and we could calculate how good that compression actually is. And I see somebody's already typed in the keyword into the chat, and this is what's called an autoencoder. Okay, what you're taking is your input and you're trying to compress it so that it's actually almost always a much denser representation, and trying to predict back to the same form. And what you discover is this thing in here is a wonderful compressed representation of your 10,000. And so now you don't have to actually represent your documents with 10,000 different zeros and ones. What you can do is you can represent with, say, 300 floating point numbers. And you can stuff that into whatever your downstream classifier actually is. And that could be a linear regression, or it could be naive Bayes. It could be a car tree. It could be another neural net, okay? And this is often referred to as word embeddings as well, especially if this is a word or representing a word, you end up with a compact, dense representation, can actually be both efficient so that all your machine learning stuff learns quicker because you don't have 10,000 random zeros and ones, even though there are quite good representations for sparse arrays in most programming languages. This 300 is just more efficient. What's more, it's often better than what the expanded form is, because the errors that it makes often shares data. So if you're representing some word here like tall, what you find that it might be most confusable or most similar to a word like height. And these words are related, and they may appear saying different question. How tall is Mount Everest, and what is the height of Mount Everest? If you ask what is the height of Mount Everest, and the answer is in your document says something like Mount Everest is the tallest mountain in the world at 29,003 feet. That's wrong. When I went at school, that was its height, but it's actually higher now, but I can't remember what it is. Not because it's got higher, although it has a wee bit, it's because they miscalculated it the first time they did it way back. But you get a distance metric between your representations between different words. And then somebody, particularly this guy called Mikolov, he was at Google and had a paper in 2011, 2012, where he said, well, actually you can get distance metrics in that compressed domain, and the distance between these forms, at first he looked at Euclidean, but discovered that cosine difference actually is quite good. What you discovered is actually things that are similar are close to each other, okay? So things like dolphin and porpoise, or do you say porpoise? And I never know about that. I have in my dialect of English, the thing that's not a turtle, a tortoise, I think you say, is called a tortoise. So I don't actually know whether porpoise or porpoise is its name, but we'll find out. But porpoise and dolphin are actually close to each other, okay? And SeaWorld is close as well, because SeaWorld is, well, no, SeaWorld often appears in contexts that dolphin appears in. And things like Paris, London, Berlin all appear closer to each other, and they're closer to each other than what these other words are. So there's some distance metric thing. And wait. So I now get a representation where I can get a distance metric between words which are similar. That's incredibly useful, because if we do the sparse representation of words, where we just have zeros and ones, okay, dolphin and porpoise are completely different, and their dolphin and Paris are completely different in the same distance. And that's not very useful, because we do feel that dolphin, whale, porpoise are somewhat closer to each other than the word Paris, okay? This dense representation for words or word embeddings is actually very important, and we'll actually have a full lecture about this. But the reason I'm talking about it now is because I'm sort of talking about how neural networks have developed from the simple perceptron to the neural network 1 level, okay, which is actually really sort of linear regression, but the way we find the weights is different, to multi-layered, especially when we do autoencoders, to try to reduce the number of features and try to find a way to do that. Now, other people are going to say, well, there's other ways to do data reduction of sparse matrices, and there are, and they are actually quite good. But typically a neural network for doing it sort of doesn't need to know much about the type of data to try to find an optimal one. While many of the other more analytical techniques, actually you need to know a little bit about the data before you can do this. So things like PCA and singular value decomposition, these you need to have particular properties of the data. Well, neural networks typically don't care, but there are advantages and disadvantages there. So how can we do complex functions? Because I just said you're multiplying by a bunch of a matrix, so weights, so it's linear. So we could also get the same thing with linear regression, okay? And that's sort of true. But we can have multiple layers. Isn't that cool? Okay. Wait, if you look at the math that goes on here, what we're going to do is we're going to have some input. We're going to multiply by some weights to get some middle layer, and we're going to multiply those weights to get to that. So we can actually say, well, what we're really going to do is we're going to multiply the weights, and we're going to multiply these weights all together. So W1 and W2 actually could be pre-calculated. Do I have a thing about that? Yes, I do have a thing about that. It could be pre-calculated, and a 3-layer neural network is just the same as a 2-layer one, but you're training it in 2 layers. And the weights would be the same. That's what math does. So there could exist a matrix that could go from here to here without going through here. And that's absolutely true, okay? So that doesn't make it nonlinear. But, and it's an important but, we can apply another function at this middle layer. And this is the interesting thing in neural nets. Well, there's lots of interesting things in neural nets, but this is the thing that makes it more than just another way of doing linear regression. Sometimes you may still like linear regression because it could be better to train, but you can actually do some other function here. So instead of just taking the value here, you can apply a nonlinear function, so a non-invertible function at that point. And sigmoid is a very common one. And what you maybe do is you make things that are the highest up to 1 and everything else to 0, or you have some threshold where you say anything above x is going to be 1 and anything below that is going to be 0. This is a nonlinear function because actually you can't do that with a linear function. You can't do that with linear classifiers. And so this makes it different. This means you can actually start learning something more complex. Now, you could say, I'm going to learn independent classifiers, take the outputs of the classifiers and learn another classifier. And that's absolutely true, okay? And in fact, we sometimes still do that because it's sometimes actually quite a good thing to do. But the advantage of doing it all in the same neural net is that you can train the weights W1 and W2 actually at the same time. And you have to do something interesting to go through, what do they call it, H1. You have to go something to do through H1, but there's a nice and interesting math that actually allows to do it that uses our friend differentiation from calculus, okay? Don't worry, there's actually a bunch of tools that actually allow you to do this, okay? The function that we can put there, okay, is called an activation function. They're usually nonlinear. They don't have to be. And there's usually a choice, a fixed choice of what they can be, because they have to be differentiable. But there are even things that are not differentiable. People have worked out ways that you can get approximates of that such that you can still do things. Why would you choose, one over the other? Well, that's a good question. And you sort of learn which ones are good. And you usually learn techniques about why ones are better than others for the particular task that you're doing, or the particular data that you're doing, or by the particular complexity of the network that you're actually training. And there's usually right ways in doing it and wrong ways. There's usually sometimes marginal ways, and every so often, like every 2 years, somebody comes along with a new function that at first everybody says, that's stupid. Why would you ever do that? And it gives better results. And 2 years later, they call people stupid for not using it. Our memories are quite short in the publication form. It's actually a little surprising. And actually, which makes you think of the first person to use the stupid function maybe did it in error, okay? And when it worked, they then justified it. I'm not saying I know anybody who is gray-haired and long-haired and bearded who might have done that and discovered something that worked that shouldn't have, and then decided to justify it. But I have not in neural nets, but I've done that in other things, because that's how you discover things. So these activation functions are, you choose between them. There's usually sort of only a fixed ones that you actually do, okay? As computers got faster, as data got better, we actually started to do more things and end up with deeper nets, okay? It's harder to train, because what you're actually trying to do is, like, the weights in W1 are really quite far away from the results in Y. So when you back propagate these weights through these multiple layers, their effect, sort of diminishes. So being able to train the weights in W1 gets harder the further they are away, in general, okay? And so coming up with good training techniques and ways to make the weights actually converge quickly is something that a lot of research was done, again, often in Jeff Hinton's group in Toronto, and elsewhere in Canada. And if you want to read interesting things about science funding, you should read about how come neural networks succeeded in Canada. And it really is the case that Montreal, Toronto, and Vancouver, and I'm not supposed to say even Edmonton, but I'll say even Edmonton, did a lot more in neural nets in the 2000s and 2010s than the rest of the world, until they became really popular. And it's probably to do with how the funding came from the government, because they maybe sort of didn't work and didn't definitely work until in the mid-2000s. There were substantial success with vision, mostly in object classification. And they were really doing well. But it wasn't until 2010 that people in speech and NLP started looking at how to be able to use these techniques for NLP. And we've come significantly further in the last 10 years with neural nets. It's definitely one of the biggest boosts to our technologies. There are other things that unquestionably helped, and that is, we've got a lot more data now than what we did even 10 years ago, and much more accessible data. We've also got much faster machines. And in fact, people have joked that given that neural nets run really well on neural nets is not, does very well on GPUs because it's mostly parallel matrix multiplication. So GPUs did really well. So if you spent the 2000s playing high-end video games, thank you. You made GPUs better because you wanted to be able to play Doom better, probably not Doom now. And this actually caused all the neural network people to be able to do things faster. There is a joke that during the 2000s, Google built the best cloud computing on the planet out of standard processors. And once they had it really, really, really efficient and working incredibly well, we all moved to GPUs instead of standard processors. So they sort of lost out. That's not completely true, but they did have a really good CPU-based cloud, and then we moved to GPUs. So there are other things as well as the improvement in the math and the machine learning, but it definitely improved things. Okay. This is all I'm going to talk about with respect to neural nets at the moment. We're going to have a lecture about neural nets itself and the techniques that are being used later on. We are also going to have a specific lecture about word embeddings, and that is deep in neural nets and non-neural nets, because we're looking at the analytical ways to be able to generate neural nets and to be able to show that things like Word2Vec and later things like BERT and BART are GPT. We'll talk about GPT-3 later. Are really good ways to represent words, and how they're not dissimilar to actually some of the analytical techniques for doing it. So today, what we did was we talked about classifiers, and we talked about the probabilistic techniques using the noisy channel. We talked about naive Bayes, which is naive and it's Bayesian and it's surprisingly good. We talked about linear classifiers and how to be able to use them. And then we looked at perceptrons, which are the base for neural nets, which are really at first approximation another way of doing linear classifiers, but only in the simplest possible way. But neural nets give us a more complex way to train that allows us to train things that are both bigger and more efficient ways of finding the weights. And once we start making things more deeper and doing things with our activation functions at the different layers, we actually can get much better classifiers. So putting in a bunch of weights, a bunch of features at the beginning, and coming out with a Y at the end with 5 different features on a often called feed-forward neural net, the simplest possible form of neural net, is very powerful. And for many tasks, that's perfectly good enough for training a classifier on things like sentiment or sorting out a few relatively easy things in a classifier. Some comment about Edmonton. I didn't say Calgary though. But yeah, that's it for today. Are there any questions? And it didn't crash this time.